Hello, I'm Oliver Birch, and this is my recording for the op-amp assignment. This here is an op-amp. It's a device with a bunch of different connections. Shown here, there's a non-inverting input and an inverting input, symbolized by the plus and minus symbol. It has two DC power supply leads, one positive, one negative. The positive one is above, the negative one is below. And it has an output and then two other specialized leads used for fine-tuning at the bottom. An op-amp works where if the voltage applied to the inverting terminal is more positive than the voltage to the non-inverting terminal, the output saturates towards the negative supply voltage, and inversely, if the non-inverting is greater than the inverted, it saturates towards a positive. This effect is called maxing out and is very sensitive, and the strength of this effect is called the gain. As shown here, an op-amp switches from one output state to another whenever there's a voltage difference between its inputs. Now when voltage is fed back from the output terminal to the inverting terminal, it is referred to as negative feedback. For example, a feedback resistor placed between the output and the inverting input, as shown in this example, conveys the output back into the input. This feedback tells the op-amp to readjust its output to value determined by the feedback resistor's resistance. The gain then is the output voltage divided by the input voltage. So if you increase the resistance of the feedback resistor, there's an increase in the gain, and if you decrease the resistance, there's a decrease in the gain. Now there's also positive feedback where the output is connected to the non-inverting input, and positive impact has the opposite effect and drives the op-amp harder in either direction. Positive feedback is rarely used though. It finds special applications in certain comparator circuits. There's one formula you will really need to know for op-amp circuits. It's the expression for an op-amp's output voltage as a function of its inputs. It has V positive, the non-inverting, and V negative, the inverting inputs, and its open loop voltage gain, which is AO. That's the gain right there. So V out equals the gain times the non-inverting input minus the inverting input. This expression is for an ideal op-amp that acts as an ideal voltage source and supplies an output exactly equal to the equation. But for real op-amps, though, these must take into account the non-ideal features of an op-amp, such as its input resistance and output resistance. To give meaning to the open-loop voltage gain expression and to the ideal and real circuits, the value of AO, R in, and R out are defined with some rules. For an ideal op-amp, the open-loop voltage gain is infinite. For a real op-amp, though, it has a finite value, typically between 10,000 and 1 million. Rule 2, for an ideal op-amp, the input impedance is also infinite. For a real op-amp, the impedance is finite, typically between 1 million to 1 trillion ohms. The output impedance for an ideal op-amp is 0. For a real op-amp, it's typically between 10 to 1,000 ohms. And rule 3, the input terminals of an ideal op-amp draw no current. This is basically true for a real op-amp as well. The actual amount of input is currently the actual amount of input current is usually insignificantly small. I have an example here. Since the inverting input, V negative, is grounded and is thus 0 volts, and V positive is R in, you can plug these values into the open loop voltage gain expression. Rearranging this, you can find the expression for the gain, which ends up being V out over V in. Now more on negative feedback. Negative feedback is the wiring technique where the output voltage is sent back to the inverting terminal. This voltage can be sent back through a resistor, capacitor, or complex circuit, or can simply be sent back through a wire, and it changes the formula a little bit. There's really only one formula you need to know for negative feedback circuits, and it looks a lot like the previous one, V out equals gain times the inputs. There is, however, the V negative or inverting input in the formula you must consider. V negative in the formula changes now because the output voltage from the op-amp is giving extra voltage back to the inverting terminal. What this means is that you must replace V negative with FV out, where F is a fraction of the voltage sent back from V out. Since you're dealing with negative feedback, you can apply Rule 4, which says that the output will attempt to make V positive minus V negative equal to 0. By examining the simple connections, notice that V in equals V positive and V negative equals V out. This means that V in minus V out should equal 0. Rearranging this expression, you get the gain, which is V out divided by V in, which will just equal 1. A gain of 1 means there's no amplification at all. Now for positive feedback involves sending output voltage to the non-inverting input, which is V positive. If you look at the previous gain expression, V out, or if you look at the previous expression that we rearranged to get gain, V out equals gain times V positive minus V negative. The non-inverting input, V positive, term changes to F of V out, just like just like the negative input turned to F V out previously. So you get to V out equals the gain times, in parentheses, F of V out minus V negative. This is similar to the equation for negative feedback. Now, an important thing to notice about this equation is that the voltage fed back to the non-inverting impact will act to drive the op amp harder in the direction the output is currently going. Recall that the negative feedback acted in the opposite way. The FV out term subtracted from the expression, preventing it from maxing out. For most applications, it's desirable to control the gain, while it's undesirable to go to the extremes. There is, however, an important use for positive feedback when using an op amp to make a comparator. Positive feedback can make output swings more pronounced. Also, by adjusting the size of this resistor, the feedback resistor, a comparator can be made to experience what's called hysteresis, which is this effect right here, where it gives the comparator two thresholds. The voltage between the two thresholds is called the hysteresis voltage, and by having two thresholds instead of one, the comparator circuit becomes more immune to noise that can trigger unwanted output swings. So as shown in the diagram, it activates when it goes below the first threshold, and then it only switches outputs once it goes above the second threshold, meaning that if it were to spike up and down, it wouldn't be turning on and off quite as rapidly. Now for the different kinds of op amps, the first kind is general purpose op amps. There's a huge selection of op amps out there. Unlike general purpose, precision op amps are designed for high stability, and you'll find op amps that fall into one of the following categories based on their input circuitry. There's bipolar, JFET, MOSFET, and some hybrids thereof, like BiFET, which is bipolar in one of the FETs. In general, bipolar amps have higher input bias currents than either JFET or MOSFET, and this means that their input terminals have a greater tendency to leak in current. Input bias current can result in voltage drops across resistors of various networks, which in turn can offset the output voltage. So the amount of offset a circuit can tolerate depends on the application, but usually you want as little as possible. Next is those precision op amps, and a simple way to avoid problems associated with input bias current is to use a FET op amp. A JFET op amp has a very low input bias current. Though FET op amps have lower input bias currents than bipolars, there are other features they have that aren't quite as good. For example, JFET amps often experience an undesired effect called phase inversion, where if the common mode voltage of the JFET approaches the negative supply too closely, the inverting and non-inverting terminals may reverse directions. Negative feedback goes positive, causing the op amp to latch up. It's usually best to concentrate on the specs listed in the electronics catalog. Characteristics to look for can be speed, noise, input offset voltages, bias currents, common mode range, gain, bandwidth, etc. For programmable op amps, they are versatile devices used primarily in low-power applications like battery-powered circuits. They can be programmed with external currents for desired characteristics. Some of the characteristics that can be altered by applying a programming current include input offset and bias currents, the slew rate, gain bandwidth product, and noise input noise, all of which are roughly proportional to the programming current. These programming currents allow the op-amp to be operated over a wide range of supply currents. Because a programmable op-amp can be altered so as to appear as a different op-amp for different circuits, it's possible to use a single device for a variety of circuit functions within a single system. Then there are the single supply op-amps, and these op-amps are designed to be operated from a single positive supply and allow input voltages all the way down to the negative rail, normally tied to ground. They are frequently used in battery-operated devices. And lastly, there are audio amplifiers. These are closely related to conventional op-amps, but specifically designed to operate within the audio frequency spectrum, which is around 20 to 20,000 hertz. And they're used in sensitive preamplifiers, AM/FM radio, servo amplifiers, intercom, and lots of other audio circuits. Now, there are a bunch of different op-amp specs to be aware of. For example, there's common mode rejection radios, CMRR, and it's the input to a difference amplifier contains two components, common mode and a difference mode signal. The common mode is the average of the two inputs, whereas the difference mode is the difference between the two inputs. Ideally, an amplifier affects the difference mode only, however the common mode is also amplified to some degree. The CMRR, which is defined as the ratio of the difference signal voltage gain to the common mode signal voltage gain, provides an indication of how well an op-amp does at rejecting a signal applied to both outputs. The greater the value of CMRR, the better the performance of the op-amp. There's also differential input voltage range, which is the range of voltage that may be applied between input terminals without forcing it to operate outside its specs. Differential input impedance is the impedance measured between the two input terminals. Input offset voltage is the output voltage of an op-amp should be zero when both inputs are zero. However, a slight circuit balance within the internals can result in output voltage. The input offset is the amount of voltage that must be applied to one of the inputs to zero the output. There's also input bias current. Theoretically, an op-amp should have infinite input impedance and therefore no input current. However, small currents may be drawn in by the inputs. The average of the two input circuits is referred to as the input bias current and can result in voltage drop across resistors in the network and can lead to errors in the output. Input bias depends on the input circuitry. With FET op-amps, input bias is usually small enough not to cause serious offset voltages, but bipolar op-amps may cause problems. Bipolars, a compensation resistor is often required to center the output. Then there's input offset, and is the difference in the input currents into the two input terminals when the output is zero. The input terminals of a real op-amp tend to draw different amounts of leakage, even when the same voltage is applied to them. This occurs because there's always a slight difference in resistance for the two terminals that comes from the manufacturing process. Therefore, in op-amp's two terminals are both connected to the same input voltage, different amounts of input current can cause the output to be offset. Then there's voltage gain. A typical op-amp has a voltage gain of 1,000 to 100,000. However, the gain drops to 1 at a frequency called the unity gain frequency, typically from 1 to 10 megahertz, a result of limitations of the op-amp's internal circuitry. Output voltage swing is the peak output voltage swing that can be obtained without clipping, and slew rate is the maximum rate of change in an op-amp's output voltage with time. At high frequencies, the magnitude of op-amp slew rate becomes more critical. So general purpose op-amp, like the 741, has a half volt per microsecond slew rate, a relatively small value when compared to higher speed models that can get to 600. And lastly is the supply current, and is the current that's required from the power supply to operate with no load present and with an output voltage of zero. Now for powering op-amps, most op-amp applications require a dual polarity power supply, but if using batteries, one of the following arrangements can be used. It's often best to avoid split supplies. One option, though, is to use a single supply op-amp. These devices will clip the output if the inputs attempt to go negative, making them unsuitable for AC coupled applications. To avoid clipping while still using a single supply, it's possible to take a conventional op-amp and apply a DC level to one of the inputs using a voltage divider network. This in turn provides a DC offset level at the output. With the input voltage offset in place, or with the input offset to voltage in place, When an input signal goes negative, the voltage applied to the input of the op-amp will dip below the offset but will not go below ground. The output in turn will fluctuate about this offset level, though to allow for input and output coupling, input and output capacitors would be needed. And now for comparators. In many situations, it's good to know which of two signals is bigger or when a signal exceeds its predetermined voltage. In the non-inverting comparator, the output switches from low to high when an input voltage exceeds the reference. In the inverting comparator, the output switches from high to low when the input exceeds the reference. In the far left, a voltage divider is used to set that reference. So you can see here, the output is high when the voltage crosses the reference, and it's the opposite in the other one, where it's high when it's not, and it goes to low when it does cross the reference. Another more popular method for comparing two voltages is to use a special IC called the comparator, like right here. Comparator is an op-amp, or the comparator, like an op-amp, has an inverting output, a non-inverting input, an output, I misspoke, has an inverting input, a non-inverting input, an output, and power supply leads, and is schematic, looks like an op-amp as well. However, unlike op-amps, comparators are not frequency compensated and therefore cannot be used as linear amplifiers. And in fact, comparators never use negative feedback and often use positive feedback. Negative feedback where using a comparator, its output characteristics would be unstable. Comparators are specifically designed for high-speed switching and have much larger slew rates and smaller propagation delays than op-amps. Another important difference is that between a comparator and op-amp has to do with the output circuitry. Unlike an op-amp, a comparator uses an internal transistor whose collector is connected to the output and whose emitter is grounded. And when the comparator's non-inverting terminal is more positive than the inverting terminal, the output transistor turns on, grounding the output. When the non-inverting terminal is more negative, the output transistor is off. Comparators are commonly used in analog to digital conversion. Typical use might be to connect a magnetic tape sensor or photodiode to an input of a comparator and allow the sensor to drive the comparator's output to a low or high state suitable for logic circuits. And that's the end. Comparators were the last thing to cover, so thank you for listening. Goodbye.